balance out. All right, so I might give my balance. Need to make sure that it is actually zeroed, because again, if it's a little bit off, if it's off by 0.1 grams and this has a mass of 0.2 grams, you're introducing a 50% error right then and there. A little bit off, let's see, so I need to take it that way. That works. Actually, I want to redo that because that was not all the way on zero. Yeah. Seems to be getting a little stuck. All right, so now find the mass of this. Come on. All right, so we have a mass of 1.14 grams. The length slightly more than a meter. Uh, 1.06 meters. Now, to put it into the nice units so that we can do our calculations a little bit more easily, we'll take that mass into kilograms. So our linear density is 0.00114 kilograms divided by 1.06 meters. And we end up with, if someone would be kind enough,
0.0011.
try it again. Say it again.
0.0011.
Like that?
Yes.
Kilograms per meter. All right. We have a linear density. The tension in the string, well, I've got this mass hanging right here. The tension that's holding this up should equal the tension, or should equal the weight of this mass. And so if we find the mass, we can figure out what the weight is. We are assuming that the tension is constant throughout this, because if it is not, then it invalidates it all. And it is pretty close. When you get to the higher harmonics, the weight of the string starts to have more of an effect, but we'll just slip that off, put it onto the balance. And I know it's going to be, should be just shy of 200 grams. A little bit drier than I was thinking. Oh, wait, no. I was going the wrong way. There we go. So 193.6. So the hanging mass, 193.6 grams, which would be 0.1936 kilograms. I need to find the tension. This is not a force, so it should be equal to the weight. So the weight that's hanging, 0.1936 kilograms, times acceleration due to gravity, mg, 9.798 meters per second squared. And someone be kind enough.
1.8973.
Units?
Students.
Yeah. Or if you wanted to go with what you had here, kilogram meters per second squared, works. Joules per meter also works. All right, so I now have the tension of the string. I have the linear density. So let's find out what the speed is. Probably don't want to use that on that board. Speed is the square root of the tension over the linear density, which is the square root of 1.8973 newtons, divided by our linear density, 0.0011 kilograms per meter. Therefore, what is the speed of the wave?
Uh, 41.531
41.531.
meters per second.
Thank you. All right, anyone else get the same thing?
I got the same thing.
All right, so we have how fast the wave is traveling along the string. I know that was the third harmonic, right here. So I know the wavelength is 2/3 of the length. So we need to figure out what the length is. And doing just incredibly precise measurements here. Because my hands are like a rock. So that would be 135.4. L is 135.4 centimeters, or 1.354 meters. I know that my wavelength for the third harmonic is 2/3 L. So 2/3 times 1.354 meters. So, yes.
0.903.
And 0.903. Is that percent
Yes.
units?
Hertz.
Not for wavelength.
Meters.
Yeah, just meters. Meters is the only unit I have here. That 2/3 is just the number. All right, so 0.903 meters. Well, I know that the speed is also equal to the frequency times the wavelength. So that's the frequency times 0.903 meters. And so my frequency should be 41.531 divided by 0.903. This is meters per second. This is meters. We're gonna come out a little low here, I believe. You know, there's always that hope for different. The actual answer is 60 hertz, because that's the frequency of the electricity coming out of our sockets.
So
Now, sorry, question?
why would it be that low?
Is a question of, did I get the right string there? So I'm looking at the string now. It doesn't look like this string, and it doesn't actually look like that string. I think our density is wrong. So if I took this, I stretched it. No, it's still, I think our linear density is wrong. I think I got the wrong string. No, that's too thin. So that's my speculation. Thought I could take a shortcut there. Apparently not. All right, we'll come back, and I am curious to see what the linear density of that string specifically is, but I want to do something else before we start taking it apart and cutting things. If I want the first harmonic, do I increase the tension or decrease the tension? Decrease? Yeah, there were two people for decrease, I think? A vote of 2. All right, so I have, this is the 200 grams, so we know that it's a little bit less to get the third harmonic. Turn it on. All right, to get the third harmonic, just push up just a little bit. All right, so to decrease, so if I put 100 on there, we should have fewer, lower harmonic. Now, obviously, we're not at a standing wave right there. We're sort of a mixture of things. That's back at the third harmonic. I suppose I took that off and just went there. Ooh, there we go. What harmonic is that? Give me 9. I think it's the 9th harmonic. So we got, what's the antinodes? We got 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so by putting less tension on there, we have a lower harmonic. So to get a higher harmonic, and this is where the source of the profanity, what happens if I put 1,000 on here? This starts to move. Let's put 1,500 on there. Sorry, my first harmonic, I got 1,500 grams on there. That looks like that's pretty much hitting peak value there. Little bit off over here. The node seems to be somewhere around here, except actually at the vibrator. More tension. To get the higher harmonic, recognize it's interfering with itself. To get the higher harmonic, that means we got to be interfering faster than we are here. So to get the higher harmonic, we need the wave to be traveling faster, which means greater tension. Questions to hear? Then I'm gonna go ahead and figure out what the linear density of this string is to see if we actually got a lot closer to 60 than I was imagining. And we'll just do this the quick and easy way. All right, so my length is 1 meter to there. So my length is 148.9. 148.9. And the mass of this
So if the strings made of the same material, you can take the same weight, you can say if it's made from the same material, then you just have to find the length and mass of that specific string, the density will be the same.
Yes.
It'll be the same both.
that is the assumption that we're working under right now. All right, so I have a mass of looks like 0.98 grams. So we definitely do have a different linear density. So 0.00098 kilograms divided by 1.489 meters.
.0066.
Should be 3
Zero,
zeros.
66.
Again, 66.
Yeah.
That's kilograms per meter. And so that changes this number right here, 0.00066 kilograms per meter, which changes that number. What's the new speed?
53.62.
52.62.
53.62.
53.62. All right, meters per second. My frequency, my length, the vibrating length is still 0.903 meters, so this becomes 53.62 meters per second divided by 0.903. We are going to get significantly closer. Instead of our 25% error.
59.38.
Wow. Pretty darn close to 60 hertz. Hey, if it's a demonstration that came close to working, how about that?
You have it on video.
That's right. Years from now, when people are saying they never work. All right, that dramatic pause was for questions, not just basking in the glory of a demonstration that came close to working. All right, so that's 2 fixed ends. Obviously, we can get more sophisticated than that. 1 fixed, 1 free end. A fixed end is a node, a free end is an anti-node. So 1 free, 1 fixed. So I'm going to have a node and then an anti-node. That is the simplest pattern that we can do. This length here is L. How many waves is this?
1/4.
So L is equal to 1/4 of a wave, therefore the wavelength is 4 times L. This is the first harmonic. The next harmonic is actually not the second harmonic, it is the third harmonic. If you're looking at some old tests, I might have that wrong. I might refer to one fixed, one free in the second harmonic. I meant the next harmonic, which is actually the third harmonic. And again, adding a half wave every time. Let's see if I can draw that slightly better. And I imagine I can achieve slightly. This is the third harmonic. And how many waves is that?
3/4.
Because you add a half wave every time. That's 3/4 of a wavelength. And so the wavelength is 4/3 times L. Or again, that distance from there to there is L. Now to overcome some of this, the fact that we're skipping one, sometimes this will be referred to as the first overtone. The next one, which is the fifth harmonic, will be the second overtone, and so on. But the next one is the fifth harmonic. And again, we need to make sure I've got a node at one end and an anti-node at the other. How many wavelengths?
Two and a half.
Pardon?
Is it 2.5?
Not 2.5.